Hello everyone, I am Mariam and welcome to TechLab. In this video, I will walk you through how I build an autonomous drone in simulation to avoid obstacles and fly to a target position using MAVROS and ROS2. Let's see it in action. Before we dive deeper, let's take a moment to understand ROS and MAVROS that enabled our drone navigate and fly autonomously. ROS, Robot Operating System, is a flexible framework that provides services and tools to help developers create robot applications. Imagine you have a kitchen robot that can help you cook breakfast. You press a button, make toast. The robot gets bread, puts it in a toaster, waits, and then brings you the toast. Think of ROS like a manager for a team of little workers called Node who talks to each other by passing messages. ROS helps them talk to each other and work together. ROS gives a way to organize tasks into small building blocks. It gives a communication system that all parts of the robot can talk to each other. ROS is built around a few key components like node. A node is like a small program that does a specific job. For example, one node might control the robot wheel while another reads data from the camera. In ROS, many nodes run at the same time and work together. Another component is topic. Topics are the way nodes talk to each other. Imagine a topic like a communication channel. In a robot, many different components need to work together to achieve a task. ROS provides three powerful ways for these components called nodes to communicate. Publisher-subscriber model. Think of this like a radio station and radio. A publisher sends out a message like GPS or camera data. A subscriber listens to that topic and reacts. For example, a drone's GPS node publishes position, a navigation node subscribes to it and plans movement. Another way of communication in ROS is service client model. A client asks a question or requests an action, and a service answers with a response. For example, a node, which is client, requests to take a picture, and the service replies with the image file. Another model is action server client. In this model, a client sends a goal and action server starts the task, gives feedback while working, and finally returns the result. For example, a drone should fly to a point and drop a package. Action client sends the goal, which is fly to this point and drop the package, and action server, which is drone, flies, sends update, and tells when it's done. ROS is great at coordinating robot parts, but drones use MAVLink to fly. What is MAVLink? MAVLink is communication language used by drones to talk to ground station, onboard computers, or other systems. It sends live info like GPS, battery, or altitude. Also, it sends commands to drone like take off, land, or follow waypoints. Now we need to connect MAVLink to ROS Vault. That's where MAVROS comes in. MAVROS is a ROS package that connects your ROS system with drones that use the MAVLink protocol like Pix4 or Autopilot. Alright, now that you have got a clear idea of what ROS and MAVROS do, I want to explain you the code that I have implemented, how I send commands, how OSStar algorithm works, and how those paths translated into a real drone waypoints. Let's have a look to the code. This project shows them how to navigate a drone using the OSStar path planning algorithm integrated into ROS2 based system. It consists of 3 coordinated ROS nodes, each responsible for a specific task. So we have movement action client node, OSStar, motion coordinator, and drone control node. Let's start with the first node. Let's take a quick look at the movement action client node. We start by initializing the node and creating an action client instance for our custom movement action. This client will send movement goals in X, Y, and Z directions to the server. In the next part, when a request is sent using a send movement request, we first check if the server is available. If it is, we send a goal message and attach response. In the goal response callback, we simply verify if the goal was accepted. If yes, we proceed to fetch the result. The getResult callback handles the final confirmation whether the movements were sent successfully or not, based on the result status from the server. Lastly, feedback callback is triggered during the process, continuously updating the client with X, Y, and Z progress values. The node named the Waypoint Push node is responsible for converting movement requests into a self-GPS waypoints, applying path planning, and pushing them to the third node. We start by initializing the node and creating a client for the getWaypoint service, which is used to send the final waypoint list to the third node. We also define an action server that listens for movement goals in X, Y, Z coordinates, and once it receives a goal, execute callback is triggered. Inside the callback, the node logs and publishes the goal as feedback. Then we set up the grid with defined obstacles. But before that, we convert obstacles GPS coordinates to grid coordinates. Also, both the start and the goal points are converted into grid coordinates. After setting up, the ROS path planning algorithm is applied to find a safe path avoiding obstacles. If successful, that path is converted back to GPS waypoints. Finally, waypoints will be packed into getWaypoints request and sent to the third node. Let's now look at the final piece of the system, which plays a crucial role in translating and pushing waypoints to the drone using MAVROS. This node listens for waypoints generated by the ROS planner and prepares them in the required MAVROS format. It uses MAVROS Waypoint Push service to send those waypoints to the drone. Each waypoint includes a defined command along with associated parameters like velocity, altitude, and geographic coordinates. Once all waypoints are configured, the node transmits the entire set to the drone. Before moving to simulation part, I would like to explain shortly about MAVROS Waypoint Message. Waypoint Message is a custom ROS message that defines a single waypoint used in autonomous drone missions. This message allows us to define precise navigation points, including location, actions, and flight behavior. Let me walk you through the structure of MAVROS Waypoint Message. This message includes a frame. This tells the drone how to interpret the coordinates. For example, 1 means global GPS and 0 means the local coordinate, which is relative to the drone's starting position. Command for this 16 means fly to a point, 22 is takeoff, and 21 is for landing. The next one is current. Set this flag, let's say, or parameter to true only for the first waypoint. This tells the drone where to start. The next one is auto continue. This determines whether the drone should automatically go to the next waypoint after completing the current one. Parameter 1 to parameter 4, these parameters depend on the command. They can define things like loiter time, radius, or yaw orientation. Finally, we have the coordinates. We have latitude in degrees, then longitude in degrees, and altitude in meters. Together, this message finally defines a waypoint, its position, and behavior. Alright, that wraps up the software architecture of our autonomous drone system. We have explored how ROS nodes interact, how movement is coordinated using ROS star, and how waypoints are sent using MAVROS. In the next video, we will bring this all to life by simulating the entire setup in Gazebo. You will see how the drone moves autonomously in virtual environment using the exact logic we discussed today. Thanks for watching, and I will see you in the next video.